Morning. I guess I'd like to start with questions. How many people here are actually trying to use the G1 garbage collector? How many people are having success with the G1 garbage collector out of the ones that are actually trying to use the G1 garbage collector? I'm seeing far fewer hands. Actually, I'm seeing none. It's a new collector, so it's, obviously it takes a while to figure out, what's going on with the collector. So, because of that, first attempts to use are probably going to be less successful, but, hopefully life will get better as this collector matures. I know for a fact that the people in Oracle are very interested in hearing from people out in the field about what their experiences are, so that they can take that information back and try to make this collector actually work as well as we think it should work. Okay, so with that, we'll just start in with looking at the G1 collector. So that's my slide, mostly about me, and I do offer performance tuning training, so I think that's one of the locations we offer at. This is in conjunction with Heinz Kibbutz, if you managed to see his wonderful talk on concurrency yesterday. That was kind of fun. Recently, we just founded a tooling company called JClarity, and we're trying to deliver what I would call innovation in the performance tooling space, trying to look at the same problem, but from a completely new and different angle. Standard disclaimer, unlike the Oracle disclaimer, right? I don't have any lawyers telling me that this is the only slide that's meaningful here. However, I will say this is the only slide that's meaningful in this presentation, just to take a take from the keynote yesterday. So really what I want to do is take a look at the G1 collector, but I want to look at it from the perspective of GC logging, because I think that if you do any amount of garbage collection tuning, you're going to have to dig into the GC logs and try to understand what they're saying. And I think it's also a good way to try to start understanding what's going on in the collector, like, what is it up to, what's it doing, and when you figure out those types of things, then you can start making intelligent decisions as to how you might want to proceed in tuning it, right? So why collect GC logs? Well, we always want to collect GC logs in performance as well in production, because those are very key sources of information as to how we're going to tune the collectors. And as you probably all know, memory management can have a significant impact on the performance of your application. And so we want to make informed choices as opposed to just trying to guess about how to proceed. What is the performance impact of logging in GC? We've never, ever had anyone ever complain about how much GC logging has cost them in the production systems. But the only complaint you'd ever get is that under the old versions of the JVM, you can't roll the GC logs over, so they can sometimes get very large. And of course, that has implications with disk usage. But with the new JVM, with 7.0, we actually end up with a couple of flags that can actually help us. They can actually help us with the rollover problem. So so here's a number of flags that we have. Actually, I'll list some other flags when we get to the end of the talk. So these are all pretty well documented. As I like to tell people, if you really want to know what the latest, greatest, up-to-date flags are, you can go to the OpenJDK source code, download it, and get the globals globals.hpp file. And in that file, you're going to see pretty much every single, well, you will see every single flag that will be of interest to you right there. So as you can see in the list of flags here, I don't want to spend too much time on it, but you can see that we do have something that says use log file rotation, and we can have the log files roll over after a specified size limit, and that sort of solves the problem of the log rotation. Now, one of the things that I thought I'd do is just do really a very, very terse or quick review of the generational garbage collectors. That's probably something that people here are most familiar with. And the reason for doing this is that we really want to contrast that against the scheme of the G1 collector. And so as we realize with the generational collectors, what we're going to do is we're going to take heap, some amount of heap that we've allocated, and we're going to split that into two different areas. And of those areas, we'll take the one known as old and one known as young. And as of young, we'll take that and split that further into this type of configuration where we have Eden. So we'll have these 4 different memory pools here: Eden, Survivor 0, Survivor 1, and Tenured, right? And so objects are created in Eden, and when Eden fills up, we're going to run this thing known as a mark sweep collector. And the mark sweep collector is actually going to mark all of the live objects, and then it's going to evacuate them out into one of the survivor spaces. And then what will happen is that on the next collection, when Eden fills, we are going to mark all the live objects, move them into the other survivor space, and then we'll go and collect the original survivor space. Anything that's live there, we'll also evacuate it into S1. And then we'll play this game of evacuating into S0, then S1, then S0, then S1. And after objects have been around and have survived so many collections, then eventually we'll promote them into tenured space. And the problems really come with this collection scheme when we have to clean out tenured space. It's like what happens when that fills up, right? We no longer have this really nice evacuation technique that we can use. And there's reasons why we prefer to use evacuation techniques. And so we have to do what's known as an in-place collection. And when we do an in-place collection, then we eventually will suffer from fragmentation. And when we have enough fragmentation, then we'll probably have to do a compaction. And just like as anyone who's done a compaction on their Windows disk, has anyone done that? Painful, takes a long time. Right. Compaction here is painful, takes a long time, and that's a long pause time, right? And unfortunately, if we start looking at the cost models, what we're seeing is that the bigger heaps we get, the longer the pause time, right? And that's what people are really objecting to, right? So, in our mark sweep review, just briefly here, right, we're going to meet some condition to trigger a collection cycle. We're going to take all the application threads, and I'm going to change the name of an application thread now to a mutator thread. From a garbage collector point of view, that's a thread that's now mutating heap on me. Right? I'm going to take it to this thing called a safe point. And what a safe point is this activity where I'm going to, essentially I'm going to block all of the threads, all the mutator threads, bring them to a grinding halt, and I'm going to do that. They're going to do this voluntarily. In other words, what's going to happen is that the code, your code is going to get salted with these calls to saying, like, should I safe point? Should I safe point? And we're going to put that into the code at places where it's safe to stop your threads. Okay? So we just can't stop them anywhere, because if we go and change heap out from underneath your thread and we have a reference issue there, then all of a sudden bad things can happen, right? So we need to make sure that your application is in a safe, or your application thread is in a safe condition in order to be halted, and then we will halt it. When they finally all come to a halt, then we can start the collection process, right? So when we need mutual exclusive access to the heap data structures, right, we'll start saying safe point. Oh, everybody's safe point? Good. Now we can do whatever we want. Go back to the safe point and release the threads. And of course, this has thread scheduling implications. This will put extra scheduling pressure on your system. Now, just as an aside, there's a lot of activities that will actually require your application threads to be safe pointed. And as an aside, there's flags you can use to sort that out if you find that that's a problem. Then we're going to go through this activity. We need to find all the GC roots. So The mark and sweep itself is, how do we collect? Well, what we're going to do is we're going to first find all of the things that are pointing to objects inside this heap space that we want to collect, and then once we found them all, then we're going to start tracing the references, and that's how we're going to mark all the objects that we can find to be live. Then, as part of the reclaim step, what we're going to do is evacuate the survivors, those that have been marked live, and then we have to go and fix all of the dangling pointers, right? We don't want to run into any pointer issues, so we have to find all of the things that were pointing to these things, and then we have to swizzle them or do something, right, so that when you go to reference this thing, right, and it's gone, you can actually find it afterwards, right? And that's a big problem that we have to face too, right? So, so what's a safe point? I think I pretty much described that in the previous explanation. But really here, we're going to block all mutators until we're finished with the data structure. So it leaves the question, like, what's a GC root? Well, as I said before, it's really a pointer outside of a memory pool. It's pointing to data inside a memory pool. It's a very, but it's not the traditional definition, but I find it's the most useful one. So the question is, where's Waldo? Where do we find GC roots, right? So if we're collecting Eden, that means we have to go into the survivor spaces, tenured, JNI, thread stacks, right? Globals, perm space. We have to go through all of these places and search for pointers for objects into the heap. Okay. Now, of course, they don't actually do this. We use some tricks in order to try to reduce the amount of work. But effectively, what it means is that this activity, which we call scan for roots, right, is coupled to the size of the heap. Right? And that's bad, because that means bigger heap, more scanning we have to do, and that's generally a pause time activity. Well, it doesn't necessarily have to be completely pause time, but in the current implementations, it tends to be pause time. And of course, we don't want to do that. We don't want to incur that pause. If with tenured, right, where are the roots for tenured? Well, they're in the same places, except for they're also in Eden and survivor. So you can see you can have these complex relationships where you have objects that may be spanning, object graphs that might be spanning tenured and Eden. And every time they crisscross, they leave basically something that behaves as a GC root. So these GC root sets can get very complicated very quickly in heaps. So what's in the pause? Well, obviously the safe pointing, right? So that means like number of threads you have, you're going to have to context switch them in and then out. And if you go into some of the concurrent collectors, then you're going to context switch them in and out several times, right? Well, of course, we have the scan for roots. We have to do the mark everything that's reachable. And then we have to do some sort of sweep and, of course, find and repoint everything. So, so what are the challenges that we're facing, right? So, where does this generational scheme break down, in other words? And really it breaks down because applications, we need to process larger and larger data sets. And that generally means that we tend to want to try to cache all of these things, right? Because, what do we have abundance of now that we didn't have before? Memory. Better to get something from memory than it is from disk. That means our live sets in heap are larger, which means that there's fewer dead things. And as you're going to see now, what's happening is that are evacuating. Generational collectors are good at ignoring dead objects. They don't do anything with a dead object, right? Everything is about marking a live object, copying live objects, right? So this is generally a good scheme, except for that if we have mostly live objects, then all of a sudden things go upside down. Yeah. Okay. So not so good. So not so good as heap size and corresponding live set size grows, right? So the question is, can we minimize MMU so that we can work with larger working sets without suffering from the pause time, right? So what's MMU? Well, that's a guarantee. That's a minimum mutator utilization. And we want to make that value as high as we possibly can, right? So the collector is going to say, we guarantee that the minimum amount of time that your application threads are going to get is X, whatever that value is, right? The larger value of X, the more scalability you have in your collector. The smaller values of X means you're going to have very, very limited scalability to garbage collect, right? And we can see that with the older serial collectors. They had very, very low MMU values, which meant that, you know, they didn't scale, period, right? And right now, I think we're hitting the limits of what we can do with generational collectors in terms of MMU, right? So there's still some efficiencies that can be tweaked out of generational collectors, but, you know, it's essentially building a faster bicycle when probably we want like a rally car or something like that, or something better. Which means a change in technology, right? So, you know, so the question is now, how do we disentangle pause times from heap size, right? And better yet, we're really good at ignoring dead stuff. Is there possibly a scheme we can use to ignore the live stuff, right? So if you have a large, stable, live working set, you know, do we have to continuously revisit the set all the time and continue to work with it, even though that we know that it's probably going to hang around for a long time? And really, the next technology that I think is, you know, maybe the rally car is this thing called a regional collector. And a regional collector is set up, the scheme is set up very differently than a generational collector, but it does share a lot of characteristics. And now I think we can see the contrast here. Current implementations, these things are sort of regional collectors. They're sort of hybrids between generational and regional collectors, and they each have their own characteristics, and that makes, you know, one better than the other. I think of the three, Azul C4 is probably the most mature. But of course, that comes with its set of constraints. IBM Balance is the newest. I don't have any experience with that, so I'm not going to make any comments on it, absolutely whatsoever. And really, this talk is about Oracle G1GC. They all, well, as I say this, there's people that are going to throw tomatoes at me for saying it, but they all work similarly the same, sort of, but not quite, right? Anyways, this is a G1 heap structure. So what you're going to do is you're going to allocate a huge chunk of memory, and we're going to divide it into approximately 2,000 uniformly sized regions. Okay? Now, these region sizes can be like either 1 to 32 megabytes in size, right? And basically some heuristic algorithms inside the JVM are going to decide how big they are. And of course, there's a flag there. I'll mention all the flags at the end, so don't worry about that. Well, sorry, I'll mention some of them. Now, the interesting thing about this scheme here is that with the generational collectors, you know, the generations had to be contiguous. We're still going to use the idea of generations in the G1, but what we're going to do is we're now going to be able to take any region and assign it to any generation that, you know, that needs to have a new region. It's going to, you know, I'm going to allocate a new region on the young generational space. So I'm just saying, okay, I want that region. Okay, and I'm going to tag it and say, okay, this is now a young generational region, right? So as it turns out, we can end up with 5 different region types. So we have Eden Survivor, Old, Humongous, and which. Heinz edited my slides, and he said humongous, which he said it was really, really, really big, because somebody commented that humongous wasn't a word that non-English speakers understood or used that much. No? Okay. So humongous means really, really, really big. Just for vocabulary. You can teach me Swedish afterwards. I'm quite happy for lessons. Right. So regions are going to be taken from and returned to this unused list, right? And since all the regions are the same. Like if you look at the generational collections, like young is different than tenured, because tenured you have to keep free lists and do all kinds of extra stuff that make them all different. These guys are all uniform. There's when they're unused, there's no distinction between old, survivor, Eden, or humongous, right? So so unused is, as I said, list of free regions. Objects are created in Eden, in one of the Eden regions. And survivor and old really serve the same purposes they do in the generational collectors space, right? So I'm going to create in Eden, I'm going to move to survivor, I'll bounce around in survivor for a while, and eventually I'll get tenured into a tenured space. Now, if I try to create a large object, something larger than 50% of a region size, I'm going to declare that to be humongous. And so what I'm going to do is I'm going to take contiguous regions, string them together, like if I make, I think Simone said, what happens if you make an array that's like 2 gigs in size, right? Like the max size int array I think you can make. Well, then in that case, I'm just going to take a whole bunch of regions, stick them together, and I'm going to use that one space for allocating that object into. So that becomes one contiguous space. I'm also going to add some other things in here. I'm going to add this thing called a remembered set. So in the generational collectors, one of the tricks they used to mark, to collect GC roots was to use this thing called a card. So every time you did something in a memory pool, and you were external to that memory pool, what you would do is you would register that activity in a card and you'd mark the card dirty. Okay? In a remembered set, what I'm going to do is I'm just going to collect cards. I'm going to do the same thing. So anytime I do something inside the memory pool, I'm going to register that pointer value or whatever in the card, and I'm going to have these cards collected in these things called remembered sets. So they're going to track pointers, right? So now instead of having to search all of memory for these things, right, I can just go and look in the cards. Now, in the remembered sets. And it gets a little better than that, right, too, because since if I'm mutating a card, I'm going to mark it dirty, I don't have to look at all the cards. I just only have to look at the dirty cards, right? So I'm going to use some tricks here to try to reduce the scan costs. Every time I write, I need to make that write visible to everybody else, and that means I need to pass through a write barrier. Right, so that's a visibility thing, right? And of course, there's an extra cost for indirection in this case. One of the things that the G1 wants to do is it wants to give you predictability, in pause time predictability, right? So you can specify, I don't want to pause any longer than, I don't know, 100 milliseconds or something like that, right? Which is generally good enough for a web app. So how does it meet those guarantees? So when it's actually doing the mark, going through the mark phase, what it's going to do is it's going to identify regions that are ripe for collection. In other words, they're mostly dead. So I'm going to calculate a liveliness factor for a region. And when the liveliness factor gets to a certain percentage, well, let's roll back on that, right? And just say that as I collect the regions, what I'm going to do is I'm going to order them by liveliness. And I'm only going to make my collection set as large as I can, I'm going to put enough regions in the collection set to cover the pause time allowance that I've been given. Okay? And then anything else, I'll get it next time. I'm not going to worry about it now. Okay? So that's really the role of the collection set, is to try to build some prediction capabilities into the collector. Now, it's not a guarantee, and if your allocation rates go really high, of course, your collection set will have to be bigger, and that will cause longer pause times than what you specified. But you get the sense here that, okay, we're going to, since we're ignoring dead objects in this collector also, and we're using an evacuation policy, just like we did with Eden, our young generational spaces in the CMS collector, or sorry, in the generational collectors, that we can take advantage of these techniques here even in tenured space, in old generational space, where we didn't really have that possibility in generational collectors. In terms of G1 phases, in the young gen, we're going to do a mark and sweep. And again, we're going to evacuate all reachable objects to a new region, a new survivor region. And this is going to cause what's known as a per region evacuation pause to occur. Right? Now, with some of the characteristics we have here, like I said, that we want the G1 to be mostly self-tuning. We really only want to be able to specify a max heap size and a pause time goal, and we want the collector to figure out everything else on its own, right? And so what it's going to do is, like in terms of how big these spaces are, it's going to try to resize them, right, by basically getting rid of regions and taking them off the table, or adding regions to try to meet our pause time goals. To do that, we're going to perform a mostly concurrent mark sweep. So we're going to have a mixture of phases where the garbage collector will be running alongside our application threads, our mutator threads, and there will have phases where we're just going to have to stop the mutator threads from doing anything. So one of the things that you can see here is that we have young gen is mark and sweep. Old gen is going to be mark only. The old gen regions will be collected by the young gen collector. So the old gen regions will become part of the collection set. Right? And it's a fully evacuating, which means unlike what we had to do with generational spaces, where we had to do a compaction step, there's no more compaction here. It happens with the copy. So, what does all this look like in a GC log? Okay. Don't try to read this. It's a warning now. We'll go through the bits, but it's very verbose. But it's a very small snippet of what you get in a log, right? So this is a GC log that's reporting one collection cycle for a young generational collection, and you can see it's reporting on all of the little phases that are happening in between. And so it's very verbose, but we can actually use this verbosity to try to sort out what's going wrong when things actually go wrong. So if you go from top to bottom, you can see that this is suffering from a pause time here. So this is a printing with details, and I'm also printing the information about the survivor spaces, right? So this is a pure evacuation pause of young gen, right? And you can see in the pink color, I'm reporting on the pause time. And that's one thing that we want to track. We do want to track pause times in this case, right? In terms of what we're reporting on in terms of the survivor spaces, we're saying that the desired or the configured, the size of the survivor space that we want is the number in yellow, 524.288. You don't mind if I don't repeat numbers, I'll just give colors. Then we're going to get a breakdown by age, right? And age in this case is how many collections have we survived, right? So at age 1, we had 82912 bytes surviving. At age 2, we had like a lot more bytes surviving, 230,888 bytes, right? But the total on the right-hand column, right, must be less than the desired size. If it's larger than the desired size, then we're going to have to prematurely promote all of these extra bytes to tenured space, right? So we can't flood the space, in other words, so that we have to do something with the overflow, and that'll go to tenured. And the indication of that condition is in the two numbers there, new threshold and max threshold. So the default survivor tenuring threshold for G1 is 15. That means I'm going to copy back and forth in the survivor spaces 15 times before I promote. And in this case, the engine came in and calculated that that was a suitable threshold, so I'm not going to change it. This particular record, a portion of the record here, reports on Eden space, right? So it's basically giving the occupancy before and the configured size before the collection. And then it's giving you the occupancy afterwards and embraces the size of the space after the collection, right? That's in the yellow. We're going to report on survivor by just saying, okay, we have the size, the occupancy before and the occupancy after. And then we're going to have total heap in the green, right? So we're going to report on occupancy before, the size of heap before, 10 megs, occupancy after, and again, the size of heap afterwards, which is 10 megs. So the heap size hasn't changed, and the occupancies, well, have gone down a bit. If you want to know what happened in tenured space, then of course, we can subtract Eden and survivor from total. And that'll tell us what's in tenured space. So that's a calculation that we can actually do. Right. So getting into the other records, you can see I've sort of grouped them by color here. And we'll just go through a bunch of the colors here, right? Here we can tell how much time we spent in parallel, which is maybe not so interesting. But this record here is probably a little bit more interesting. This is a better breakdown of what all of the GC helper threads are up to, right? This is when they started, and this is when they ended. And strangely enough, they give you this average min-max diff on when they started. I'm not sure how that's useful, but yet, quite honestly, I'm sure there's some use to it. But in this case here, you can actually see if there's threads that have been started late or threads that have ended late or something along that lines. And occasionally when these things happen, it's because of scheduling threshold pressures or there's some other activities inside the operating system that can cause some difficulties here. In this particular here, right, to finish off the record, we're going to look at the total concurrent time from start to stop, right? So this is, now what's interesting here is that when the collector is running concurrently, it's going to try to give half the time to your mutator threads, and it's going to take half the time, right? And in most applications, this doesn't really matter. You tend to have enough CPU that this behavior is actually really good because it's just soaking up CPU that you're just wasting, right? But sometimes this can be a problem, and you'd like to know how long these things are running to try to see if you can shorten the cycle durations. Per thread time to scan for roots. And again, this is an indication of like how difficult it is to find you find your root sets so that you can start your initial scan or the initial phase of the mark phase. Here we have basically we're going to update some processing buffers and update remembered sets as we're doing work. And mostly what we're trying to do is we're trying to set ourselves up now for defining the size of the collection set so that we can go into the mark phase. Per thread time to process the remembered sets. Right? So now we're copying objects in this phase, so we're into the evacuation phase. And of course, as we're copying the objects, we have to update the remembered sets, and we have to go through the whole allocation process in some other region, the target region that we're copying to. And then we have a termination step. Inside the termination step, what we're saying is like, okay, the thread's going to come to the end of its workload, and it's going to say, okay, I'm going to stop now, unless there's something else for me to do, right? So it's going to offer to stop, and then it's going to look, and the process is that it's going to look at other threads working, workloads, and say, okay, can I steal work from them? And if it can still work, it'll still work from the other thread, keep going, and then it'll, once it finishes that, offer to stop again. So if you look at this, you see there's a line down there called termination attempts. So this is the number of times that work stealing really has been successful. Then there's some miscellaneous things on the end here. We have to clean the cards, right? These cards are inside the memory set, remembered set, and that's going to be a pause time event. And there's a number of other tasks that are basically cleanup tasks, with the exception of the reference processing and the reference and queuing. So this is where we do finalization, or well, weak reference processing, phantom reference processing, soft reference processing, things like that. Okay? And that's pretty much what a young generational collection looks like, right? And this particular record here, you can see that it's slightly different in the sense that if we look at the top of it here, it's probably hard to look at in that small slide, but you can see that instead of just having the straight pause time like we had in the initial record, in this case here, we also have this bracket initial mark in here. And this is the beginning of the old space collection. So what we're going to do is this is an evacuation. These are the evacuation pauses. So in addition to pausing for the evacuation, we're also going to trigger the initial mark of the tenure spaces, right? So that's trying now to build a, find all of the root sets that we can actually use for starting to mark all of the live objects in tenured space. Then we're going to go into a number of concurrent phases. So remember, your mutator threads are running while we're running concurrently, which means that the picture of memory is changing while we're running the collector, right? So what we're going to try to do is we're going to try to go back and find the remembered sets that have been mutated, well, the cards that have been mutated, and after we've done our initial mark, and we're going to try to do a remark to capture things that have become dead since we finished the initial mark, right? And we're going to try to do this a couple of times, and then when we're finished that, then we'll finally go into a final remark phase, and this is the stop the world phase again, right? So we want to try to make this remark phase as short as possible, and in order to do that's why we're doing all the other work concurrently. And here we're going to try to set ourselves up to try to make this pause really, really short, right? And this will do the final remark. Now, it's not going to capture everything, but it should capture mostly everything. And what it doesn't capture will be captured in the next collection cycle, which is a similar story to CMS. And finally, we're just going to do a concurrent cleanup, and the concurrent cleanup is really just putting the regions back into unused. There's a few other records, and you can get a lot more details, but I think this is probably good enough detail for now. But in the other records, we can have something that looks like this. And this is really an indication that your heap is too small. So basically, we're going to put all the work that needs to be done into this thing called the global marking stack. And if we fill it up, that means that we've had to mark too much stuff, which means we've probably started the collection too late, or the heap is too small. And so that's one of the corrective actions that we can do. We can make heap bigger, or we can start looking at flags that we might be able to use here. And in this case, for that particular problem, I'll just skip ahead to this one and say that's initiating heap occupancy fraction, right? Right now it's defaulted to 45%, which means that when the heap gets 45% full, that's when we're going to start that's a trigger to start a collection. And in some cases, we might say that 45% doesn't give the collector enough time, right? Because it's in a race condition with your mutator threads. It's trying to clean out memory. Your mutator threads are trying to fill up memory, right? If it loses the race, it's got to take corrective action, right? So in this case, what we're going to say is like, okay, if we reduce that number, then we're going to trigger the collector to start sooner, which gives it a head start or a better chance to win the race. In terms of other flags here, again, we can set max heap, min heap. We can set our pause time goal. That's really the second thing up there. And we can specify that pause time goal over an interval. I'll talk a bit about that in a second. Oops, sorry, there was an extra slide in here that didn't get deleted. Okay. New ratio defaults to 2. What that says is, in terms of how do I partition the sizes between how much goes to tenured and how much goes to young space, or even the survivor spaces, right? So that's going to be meaning that I'm going to divide the space into 3 regions, and young is going to get 1, and tenure space is going to get 2 of those. A similar calculation for doing survivor ratio. What we're going to do is that we're going to divide, very similar to tenure, we're going to divide the young generation space up into 10 chunks, and we're going to say that survivor 0, survivor 1 get in CMS, they would each get 1 chunk, and then the Eden would get 8 chunks of it. So that's how we proportion memory. Unfortunately, we're still using ratios because I just did an engagement where I figured we wanted a 10 meg Eden and 20 meg survivors, and of course that configuration is completely impossible using this ratio. Right, the best I can do would be 10, 10, 10, or 20, 20, 20, right? But 20 was giving us too long a pause time, and having survivors at 10 megs was causing other problems. So there's a number of different flags here. What I can say about the flags is that if you start trying to self-tune this collector, you start turning a lot of things off, and then you find that you're going to have to tune everything. Okay? So really the only things you can touch safely are max heap size and the pause time and the pause time interval. Right? Once you start going into the other fine-tuning, right, they basically say, okay, it's your job now to tune the collector. Right? And I'd really don't like doing that because that means the collector becomes less adaptive to runtime conditions. So I really try to avoid tuning by setting a lot of flags. So we just want to be very light on the flags. Don't be too aggressive with pause time goals. That'll cause a lot of failures. And if you have a lot of failures, that means that you have to do a lot of work over again, and then you tend missing your pause time goals more often than if you just had slightly less aggressive settings. And I would just say this, my experience so far has been it's a very, very difficult collector to tune right now. If you can get it to self-tune, then of course, that's obviously a much better place to be in. Mostly I would say is that we just don't have enough experience tuning this thing. And there's some other tuning parameters that I failed to mention in here that have to do with waste percentages and things like that, that really seem to affect some of the pause time events, the duration of the pause time events. So you can get long pause times that are related to some really strange internal mechanics as to how they record things and how they deal with things. For instance, the card system, it sounds like it's a very single-tiered thing, but actually there's 3 tiers down there. And card densities can have a real effect on scan times. So it gets to be kind of problematic. So just to let you know, it's like, how good can we do with low latency? I'm sorry that this thing is sideways here, but if this is an oscilloscope hooked up to a photocell on a monitor, and we're just basically flipping the screen color, you can see every time the waveform flips, that's a GC pause. Right? And that's affecting the JavaFX application's ability to actually update on the vsync signal, which is like kind of fun. Right. So I really wanted to try to leave more time for questions here. I think we have a few minutes questions, maybe not as much as I wanted to leave behind. But anyways, I am open to questions. Please shout them out, and I'll try to repeat them for people who are interested in the question. Yes, sir.
About objects which are not changed from the main method start to until the end, long-living objects.
Long-living objects, yeah.
Could it be a good idea to let the programmer tell objects that they are long-lived? So
it's never a good idea to let the programmer fix an object life cycle because they tend to, well, I mean, the classic example is perm space, right? Perm space was intended to be a place where everything that was to be around for the lifetime of the JVM, we'll put it there, right? And it's like, how well did that work out? How's that working for you? As a matter of fact, if you look at JDK 8, there will be no perm space. It worked out so well, right? Anyways, so yeah, I think in this case what we were hoping for is a collector that would ignore the dead objects because they would end up tightly, densely packed into old gen regions, and the old gen regions would just be put up there. But unfortunately, we haven't really disentangled ourselves from the heap size because we still need to do the scan for roots, which means that we still need to go through the remembered sets, or we need to deal with that particular region actually when we do the scan for roots. And so it still is going to be involved in some phase of the garbage collection cycle, and because it's involved in some phase of the garbage collection cycle, then we still have a, shall we say, a dependency on the total size of heap, unfortunately. So that's why at the beginning when I said almost or variant of, that's the caveat. Is there any other questions? Sorry. Yes.
I have a problem with a cache containing soft references that grows until its maximum size that takes up almost all the heap, basically.
Yeah. Okay. So he has a problem with soft references. They have in a cache that keeps growing until it takes up all the size of the heap. Are you using a G1 collector, or are you using a CMS collector, or are you using a parallel collector?
For the moment, it's an old JVM that we're upgrading, so we're going to upgrade.
Right. Okay. So there are bugs in the older versions of the JVM. I like this answer. It's not your fault. It's a bug. Right. That's right. Which may or may not be the case in this particular instance, right? But there is a parameter that you can set that you might be able to tune down that might clear the soft references quicker. So soft references are kept for a time duration of last access and a function of free heap. And do you know, Carl, do you remember the parameter? No? Okay. So it's a really strange long one. But essentially you can set this parameter. It's set for, God, what's the value? Okay, I completely lost the value. I think it's set so that you should be able to work under normal conditions, but it might be that your heap configuration is such that you need to dial that back so that it clears out soft references more aggressively in that case. But I would also check in older versions of the JVM, soft references were a real problem, shall I say, traditionally. Okay. Anything else? Oh, sorry, didn't mean to say. Yes, sir.
There seems to be a trend in using off-heap memory right now.
Oh, yes.
Do you have any comments on that?
Yes. You better trust that the guys who are creating these things, these off-heap memory spaces, know how to write garbage collectors, because effectively what they're doing is they're creating yet another object space, another heap space or memory pool inside the JVM that will eventually need to be garbage collected. And if it's not garbage collected, of course, your JVM size will grow. Heap won't grow, but the overall process size will grow. If you have any problems or memory leaks in that particular space because of this, you better hope that they're able to provide tooling to debug those situations, because then you're going to be out of tooling to do that. Aside from that, it seems like a good idea. We're done? Okay. I think we're done. Thank you for attending. Have a good rest of the day.